The first talk of the session is New MPC Techniques for Secure Machine Learning by Nishanth Chandran. And the speaker is remote, but hopefully online.
Hi. Hopefully all of you can hear me. First of all, thanks to Sophia and others at Aarhus for inviting me to give this talk at TPMPC. I was really looking forward to my first trip to Denmark, but unfortunately, despite the best efforts of Malin Anderson at Aarhus University, the Denmark embassy still has my passport for about a month, so I've not gotten my visa yet in time to come, but hopefully you guys can hear me. So today's talk is going to be about some new MPC techniques in the context of secure machine learning, and in particular, I will focus on some of the problems and use cases that we have been working on at Microsoft Research in India. Okay, so one of the main scenarios that we have been working on over the last few years is that of secure inference. And in this, we have an AI vendor on the left who has trained a machine learning model on some sensitive information, right? And has obtained the weights of this model. Typically, the model architecture is something that's public information, but the weights are sensitive information because this has been obtained by training the model on sensitive information as well, right? And on the other side, we have a hospital that has patient data. And we would like to run the model on the patient's data such that the hospital learns the disease prognosis and absolutely nothing else about the model. And the AI vendor learns no information through this entire process, right? So classical problem of secure inference. An application of this, which we have also come across in our work, is that of secure AI model validation. And it's an extension of the same framework where, again, you have an AI vendor on the left with a pre-trained model M. The hospital now has a collection of patient data, right, called the test data. And they simply want to find out what the accuracy of the model is on this test data set without revealing the test data set, right? Or they may even want to answer a very specific question: is the accuracy of M greater than some threshold on the test data set, right? So we will focus on problem one, and problem one naturally gives us solutions to problem two as well. So for the rest of the talk, you can think about this, except at the end when I'll mention some studies that we have done over here. All right, so if we wanted to solve this particular problem, in an ideal workflow, we want to make it as easy as possible for those without any cryptography knowledge to be able to use this and deploy this in their end use cases, right? So the ideal workflow would work as follows. Let F be the inference algorithm or the AI validation function or whatever that you're computing. The AI vendor has this prognosis model on the left, and then you have the hospital with patient data on the right. And what the AI vendor would do is would locally strip the model of all of its sensitive information, in particular the weights, as I told you, which is the sensitive data over here. That will be removed, and you can fill it in with dummy values, right? And that's the model structure alone. And typically, this model structure is written in a framework such as TensorFlow or ONNX, which is the popular framework of choice for machine learning algorithms, right? And you'd like to feed this into a crypto compiler that does all the crypto magic that's required. And out must come MPC protocol that must execute at both ends, right? So this is the protocol code that will compute f of w comma x securely, right? And this will take as input the weights from the AI vendor and the patient data x from the hospital. And then the MPC protocol execution will start, and whoever needs to learn the result learns it. In our particular example, the hospital learns the output of this function. Okay. And there has been a lot of phenomenal work on MPC compilers and protocols. I've listed a few here. I'm sure there are many that I've missed as well. And there are frameworks that go from C-like languages or Python or even TensorFlow or ONNX and so on for machine learning applications. So really, what is the problem that we are trying to address here today? The problem is that most of these frameworks require what is known as quantized or integer code as their front end, right? So you take floating point values, and then you want to pick a particular scale and bit length, and you say every value that I ever have is going to be represented within this range and with this particular fixed scale, and I'm going to run my entire computation with this. And as we'll see, this has its limitations, and we want to overcome these limitations in this work. Now, typically TensorFlow or ONNX code is written over floating point arithmetic. And so if you want to build an MPC protocol for this, what are our options with us? The first option is that we can provide secure computation protocols for floating point arithmetic itself. So take all the floating point operations that are there and emulate them faithfully, respect the standard of floating point arithmetic, and design secure computation protocols for that. And this has been studied as well. I'll refer you to a recent Oakland paper of ours on some of the latest work in this area for secure two-party computation that provides secure computation protocols and functionalities that are accurate as well. So they respect the standards of floating point computation as well, so that you don't lose any precision when moving to the secure world. The other option, which has been fairly popular in the machine learning world, especially for inference algorithms, is to convert floating point arithmetic into fixed point arithmetic protocols. Okay, and here we would ideally like to support the state-of-the-art automated converters that already exist. There are plenty of converters, and more converters are being written as we speak, on how to take floating point arithmetic code and convert it into fixed point arithmetic code for machine learning applications without sacrificing in accuracy and so on. And a lot of these converters exploit certain things. First of all, they vary their bit width and scale throughout the course of the computation for efficiency purposes. And if we were to disregard this information, we may actually end up losing a lot of efficiency in the MPC world. And the second point is that they actually rely on the transcendental functions such as exponentiation or tanh or sigmoid and so on to be accurately computed so that they can have reasonable accuracy of the fixed point algorithms that they output. And so ideally, we'd like to have MPC protocols that can support both of these, that can support variable bit width and scale, tiny bit widths and scales, as well as precise transcendental functions. And so the focus of today's talk will be on this particular aspect and some of the new cryptographic techniques that we have developed in this particular context. Okay, so the talk outline will be as follows. I'll first briefly describe the 2PC model of computation that we will be discussing in this particular talk. I will provide an example float to fixed converter that can give you a sense of how this mixed bit width computation looks like. I will present a high-level description of some of the functionalities that are required, such that if we support those functionalities, we'll be able to do everything that I was talking about. And then I will present some new crypto protocols for, in fact, one very specific task. I'll present new cryptographic protocols that we have that we have found to be quite exciting and very useful. And finally, I'll describe some end-to-end use cases that we have been able to execute secure inference. All right, so coming to the 2PC model, in this particular talk, we will focus on the following 2PC model, which is semi-honest security, 2PC, in the pre-processing model. And what do I mean by that? In the pre-processing model, there exists a dealer who in the pre-processing phase, where no parties have inputs, will provide correlated randomness R0 and R1 to both parties, party 0 and party 1. Okay. Then the dealer goes away. And then you have the online phase where the parties can interact with each other to compute the function f of x0, so. Okay. Now, if you're really interested in 2PC protocols without the pre-processing and standard 2PC, I will point you to the paper from last year's Oakland that we had that gives protocols for some of these tasks without in the standard model without pre-processing. Okay, Now, I told you that we're going to be working with semi-honest security and in the dealer model. You may ask, okay, what about if we don't have the dealer model and if we wanted malicious security and so on? I'll just remark over here that things can be handled. They are a little bit more expensive. If you want to get away with a trusted dealer, they are more expensive. If you want to support malicious parties, they can be done. And this has a small overhead over semi-honest security. All right, so let me now give you a high-level description of how one of these float to fixed converters work and what are some of the operators that they actually end up doing. So let's take a look at the task of the algorithm for support vector machines, which is a very popular machine learning algorithm. And this is a description of the function. It's doing some summation of CI times exponentiation values. And you have this code that's written in floating point arithmetic, and there are converters that will convert this into fixed point arithmetic as well. Now, I'll remark over here that real values are when I want to represent it in finite number of bits with some particular scale. So if I want to represent in L bits with scale S, I'm going to take R multiplied by 2 to the S, floor of that mod 2 to the L. That's the value that I'm talking about. And so one of these converters, this is how they work. Essentially, it takes as input values that have bit length of 16 and scale 12, and then start performing the arithmetic while retaining the scale. So it does the subtraction, retains bit length and scale. And now when I perform the multiplication, I naturally end up with a larger bit length and scale. So I end up with 32 bits and scale of 24. And so this converter basically truncates and maintains scale, and so goes back to maintaining scale of 12, but retains the bit length of 32 because there is a summation that's going on and I don't want things to overflow and so on, right? And now summation happens over 32 bit values with scale 12. And finally, a computation of this exponentiation happens. This happens through various means, typically through some approximate means because it's a transcendental function. And we will talk about that a little bit later on. And finally, it outputs a single bit, which is the sign, which is what I'm interested in over here. Okay. So let's take a quick look at how some of the transcendental functions are typically computed. And this will be important for us because we will discuss this in fairly detail as the talk progresses. And a typical way to compute these functions is through spline computations or piecewise polynomials, right? So I define f of x to be a collection of polynomials, and depending on where x lies in the range, I'll output of a different polynomial evaluate on that particular point x. Right? So that's how I'm going to evaluate, and observe that because I'm doing this, I need to do a whole bunch of comparisons because I need to find out where x lies in this range. And I also need to do some arithmetic, which is evaluate this polynomial. Right? And because it's an approximate version of the true function, the error of the function is important. And here, something known as ULP error or units of least precision is the gold standard, and it provides better guarantees over the more well-known relative and absolute error. Very informally, it tells us the number of representable numbers in the output domain that's between the exact real result and the output of the function. And I'll just remark over here that all functions in this work have an ULP error of less than or equal to 4. You want it to be as small as possible. Beyond this, this will not be too important today. Okay, so now when you're approximately computing some of these transcendental functions, you ideally would like to get a crypto-friendly approximation because you know how expensive certain things are to compute in the crypto land. You want to kind of maybe take that into account when you design the approximation itself. For the 2PC model and the 2PC with preprocessing model, these cost metrics are actually a bit different, as we will see. Right? In 2PC, computing spline functions accurately are expensive. You may end up requiring too many intervals, high degree polynomials, and therefore computing comparisons, and the polynomials and so on end up being expensive. And so we use a slightly different technique, use lookup tables to get an initial approximation and then iterate to get accuracy. Again, I'll refer you to this Oakland paper from last year for details on that. In the 2PC with preprocessing model, it turns out that we have work where computing intervals, that is which interval does x lie in, as well as computing the degree of the polynomial, computing of the polynomial, are nearly free. Right? There's absolute, like, it doesn't matter how many intervals you are or you have or how large the degree is, somewhat nearly free. And that's kind of really surprised us when we worked on this project. And so that will be the focus of today's talk, and therefore all of the transcendental functions we have will be directly evaluated using splines itself, because it's kind of nearly free. Okay, so what are some of the functionalities that are required to support these variable bitwidth operations as well as splines and so on? Right. Now, when I look at the state-of-the-art neural networks, there are a whole bunch of operations. I can decompose all of them into things like linear operators, which are matmul, addition, convolutions, all of those. And then you have all these other crazy functions, sigmoid, tanh, and so on, which all can be decomposed into a set of building blocks for mixed bitwidth arithmetic. And the building blocks for mixed bitwidth arithmetic look as follows. I want to be able to take as input a 4-bit value. And remember, these are going to be secret shared between two parties. So I have secret sharing of a 4-bit value. And then I want to get the same value over 8 bits. But then I want in the most significant bits of all of these should be 0. I may want that as a particular function that I would need to compute. Right? This is called extension. I may want to do truncation, which is just take the 4 most significant bits of whatever I'm interested in computing and then right shift the whole thing so that they sit in the least significant bits, right? And I may want to do that and reduce the number of bits at the same time as well, right? And I may also want to support mixed bitwidth multiplication. So I want to take a 3-bit value and take a 4-bit value and multiply them and get the outputs as a 6-bit value. And finally, I may also want to do bit decomposition or in general digit decomposition. So pull out specific bits or digits of the string that I have, right? So these are all the functionalities for which we do provide protocols and so on. I'll not get into all of these. These are just a sample of the kinds of things that we do, right? And I'll just remark here that all of this that I spoke about was in the context of unsigned integers. Signed operations can also be done at nearly no cost. And finally, I spoke about splines being important. And here also you can talk about mixed bitwidth splines. And this is also something that we realize, where inputs, outputs, and coefficients of the polynomials also can have different bitwidth and scale. Right? And so the functionality for this merges some of things that we saw earlier. Again, I'll not get into it so much. Okay, so now let's get to the new crypto protocols part and the stuff that is quite exciting. All right, so over here, we are going to be making use of the technique of function secret sharing to build our 2PC protocols with preprocessing. And function secret sharing, or FSS, was introduced by Boyle, Gilboa, and Ishai in 2015. And they're the following object. I can take a function f and I can split it into 2 components, f0 and f1. And I can give f0 and f1 to 2 different parties. And these 2 parties can evaluate f0 and f1 respectively on the same x. And somehow they have the magical guarantee that whatever they have evaluated is an arithmetic secret sharing of the output. Right? So whatever they have is such that f0 of x plus f1 of x is actually equal to f of x. And these f0 and f1 are known as the FSS keys, or correlated randomness or preprocessing material. Okay, so what are some of the properties of FSS schemes? First, we want correctness, and that for all x, f0 of x plus f1 of x is equal to f of x. And then we want security as well. We want that f sigma hides f in some sense. Right? So f will have associated with it some secrets, and those secrets will depend on what this function would be. And we will discuss that a bit later. But we want that f sigma actually hides the secrets of that function. Okay. And finally, we want that f sigma be compact and not exponential in the input and output sizes. All right. So let's look at a blueprint for obtaining 2PC in the preprocessing model via FSS. And this was provided by Boyle, Gilboa, and Ishai, BGI, in 2019. Let's take a particular circuit that we have over here where wires carry ring elements. Now, let's take a particular gate over here, this F gate that takes as input X and outputs Y. And let's consider an offset gate of this particular gate. And what I mean by that is for every wire, I'm going to mask it with some randomness. And this randomness is jumping ahead. It's not going to be known to both the parties P0 and P1, but only to the dealer. Right? And so I have X becomes X hat, which is X plus R, and Y hat becomes Y plus S, right? And both the parties P0 and P1 actually know X hat and Y hat, right? But they don't know S and R, and therefore the privacy of the inputs is preserved. But what is the function now that they need to compute? What they need to compute is the following function. The function that takes as input X hat, subtracts out R from it, evaluates F on it, and then masks it with S. That's exactly what they need. And if they had an FSS scheme for computing this function, we are all set, and we will just see that in a minute. Right? And FSS, we would want that the FSS scheme hides these random values R and S. Okay. So you'll take the circuit, convert it into its offset variant, and this is how it will work. In the pre-processing phase, the dealer will provide the correlated randoms, basically the FSS keys for these F0 hat and F1 hat to both parties, party 0 and party 1. And now what would happen is that, recall, FSS keys allow P0 and P1 to compute on a common input to get shares of the output. And they start off with this common input X plus R, right? And so they can evaluate on it, and they will get shares of Y plus S, right? And now if they wanted to use this in another FSS computation, they need to just reconstruct this. And if they reconstructed this, they are again back at the stage where they both hold the same input. If they have another FSS key, they can again use that for another computation, right? So this really works nicely. You can have, you can compose all of these gates together and run how much of a computation you want to. Another feature of this is that, I mean, you can go from masked inputs to masked outputs, such as Y plus S to Z plus T, or you can actually also go to from secret shares to secret shares, because you actually do get that. You get shares of Y plus S to shares of Z plus T as well. And therefore, it kind of lends itself to use in conjunction with other secret sharing based protocols as well, which is a nice feature. So the nice thing about 2PC protocols based on FSS is that if I look at the online communication and rounds, it's splendid, right? The online communication is one ring element per gate per party, no matter the function, right? And in fact, it's sent simultaneously as well. You don't even need to wait for the other party. Right? And if I look at the rounds, it's one per circuit level. It just depends on the depth of the circuit. So if I look at the online performance of FSS protocols, this looks really, really appealing. If I compare FSS-based 2PC with other approaches, let's quickly just look at per gate for commonly found non-arithmetic gates, how these costs may vary. For a garbled circuit with dealer, the online communication is also a bit high, because for every bit of input times security parameter, you need to communicate. Online rounds are good, it's only 2. And the correlation size is fairly large because you need to send the garbled circuit as well. GMW and secret sharing based schemes have the kind of opposite profile. But if I look at FSS based schemes, the online communication is really low. The online rounds is 1, right? But where it's found wanting is the correlation size. And this is a bit high, right? And while for online metrics, FSS is the clear winner over here, the biggest bottleneck for FSS is in the correlation size. And there are plenty of effects of reducing the correlation size, right? While we already had fast online phase, the high correlated randomness size ends up being a bottleneck for communicating the keys to both P0 and P1. So dealer has to communicate these keys to P0 and P1, slow pre-processing because I need to generate a lot of keys. And also online compute also may grow because I may have to compute more and so on. So in recent work with Boyle, Gilboa, Divya Gupta, Yuval, Ishai, Nishanth Kumar, and Mayank Rathi at Eurocrypt last year, we had a work on how to reduce correlation size for FSS schemes fairly significantly. And this led to faster pre-processing as well. And to give you a sense of the kinds of improvements that we are talking about, let's look at certain commonly found gates. For example, the interval containment gate. So the gate which checks if X lies in some particular range between A and B and outputs 1 or 0 otherwise. Now, if I wanted to take a garbled circuit for this, for 16-bit values, I would roughly have to have a pre-processing size of something like 15,000 bits. And the original approach of BGI 19 required something like close to 35,000 bits, whereas our work gets something very close to 5,000 bits, which about 7x improvement over the work of BGI 19. Similarly, for ReLU as well, we get ReLU, which is basically the function max of x comma 0. We get a rough 6x improvement over BGI 19. When I look at the a 12-piece spline, and this is where I told you our techniques are really shine over here, there we get a nearly 22x improvement over BGI 19 and about a 15x improvement over garbled circuits. And I'll spend the rest of the talk actually talking about spline computations and how we're able to do this in a much better manner. Okay, now it's not that FSS always wins. There is a bit of a trade-off here. You are trading off sometimes compute with communication. That is, the keygen might require more compute, but it shrinks the key size, right? So that's sometimes evident as well. For example, in 12-piece splines over garbled circuits, not over BGI 19. BGI 19 we have a hands-down win, but over garbled circuits, while the keygen's communication, there's an improvement of 15x, there's almost the opposite effect when it goes to the number of AES calls that are required, right? But if you look at runtimes, they are favorable for reasonable network settings. But the important point is that FSS-based techniques require much less storage and much faster online phase, so it could be quite appealing. All right, so let's take a look at where we are getting our sources of improvements and how we are getting them. We can split our gates into simple gates, which are addition and multiplication. We'll not discuss them today. And the more complex ones, things that do comparisons, this interval containment or ReLU or shifting and so on. There are two sources of improvement. First, we get a 4x improvement in the key size of FSS that was present in BGI 19 for comparison directly. And this we obtain by a direct comparison for a direct construction for the comparison function itself. The second one in source of improvement is that for common gates that use comparisons, we significantly reduce the number of comparisons actually needed. And that ends up being a bulk of our savings. So improvement number one, as I told you, comes as follows. So we have this distributed comparison function. So you're interested in computing, let's say beta if x is less than alpha and 0 otherwise, right? And the rough key size of BGI 19's work was something like 8 times n times lambda, where alpha and beta's lengths were n bits and lambda was a security parameter. They had a construction which was a specific case of a scheme for decision trees that they had. And by giving a more direct construction for comparisons, we are able to get roughly a 4x improvement. We get a key size of something like 2n times lambda plus n. Okay. Now, the second source of improvement is in the number of calls to DCF for common gates, right? And here, let's look at some of the improvements that we have. Right? So let's look at the interval containment or ReLU. The work of BGI 19 required 2 calls to the DCF function in order to compute it. On the other hand, we are able to evaluate it using a single call to a DCF. Secondly, if we wanted to do bit decomposition, the work of BGI 19 required roughly n calls to DCF. However, we are able to do it with n over w calls to the DCF, where w is a parameter. Of course, it's not for free over here. The compute cost required for this grows exponentially in w. So you can't arbitrarily increase w over here, but it is useful in many cases. And then, as I told you, for spline computations, and here is where our technique really shines, if I had a spline with m intervals and the degree of the polynomial that I wanted to compute was d, BGI 19 roughly required 2 m calls to DCF plus some smaller order terms, right? On the other hand, we completely remove the dependence on m itself in the number of DCF keys. We require exactly 1 DCF key plus a smaller order term. That smaller order term depends on the number of pieces of the polynomial. But importantly, we don't have something like m times lambda sitting over there. And the main observation comes from this. If I look at the gate in the unmasked world, typically the comparisons and things like that I'm doing are on public intervals. I want to check if X is greater than 0, or X lies between 1 and 5, or if it lies between 5 and 9, and so on and so forth. Now, when I apply it into the 2PC context, it ends up being, these intervals end up being secret in some sense, and I'll discuss that briefly. And therefore, BGI19 gave a construction for secret intervals where the alpha and the two endpoints could be kept completely secret. And we made the observation that this is an overkill, right? And for public intervals, if you're okay with saying what is the point that you're comparing with, are you computing ReLU, for example, which basically says X if X is greater than equal to 0 or 0 otherwise, and here the point 0 is public. Here you can do something that's much better, and that actually will be the source of our improvement. Because of that, we are able to use some new techniques of it. Okay, so the overview of our construction is going to be as follows. In the unmasked world, we start off with wanting to check if X lies between A and B, where A and B are both public. Now, when I moved into the masked world, recall I was taking every gate and then throwing randomness everywhere. And so both parties have X plus R now. And therefore, the comparison points become A hat and B hat, where A hat and B hat themselves are secret because they are now A plus R and B plus R. Right? So that's essentially what I need to compute over here. Right? And therefore, it seems like I cannot do anything. A hat and B hat are secret. I need to work with something that keeps the endpoint secret. And that's what the interval interval containment construction from prior work actually did. A hat and B hat were secret. Right? On the other hand, our construction still keeps A hat and B hat secret, but relies on the fact that B minus A can be public. For example, if I'm computing public intervals, B minus A is public. And with this observation, we are able to come up with some new techniques to evaluate these functions in a much better manner. So let's take a look at this. I'll first present an overview of the BGI19 construction itself, and then I will show you how our construction improves upon that construction. So if I wanted to compute interval containments in the work of BGI19, let's look at the construction pictorially. In the unmasked world, the number line looks as follows. And I have three regions. I have the region below A, I have the region above B, and I have the region between A and B. And I want to compute the function f that outputs 0 in both these extreme regions and 1 right in the middle. Okay. Now, when I go to the masked world, I end up having two cases. The first case is as follows. The first case is where the randomness R is such that things don't wrap around, like B doesn't wrap around. And so A hat and B hat respect their same ordering, right? And they're shifted only by a little, right? Now, in this case, only the region 3 overlaps. And the function that I want to compute looks as follows. It's 0 here, it's 1 here, and 0 here. Right? Now, what BGI19 did was the following. They gave out a DCF key for computing the comparison with A hat. And this key output -1 on all points less than A hat, right? And 0 on all other points. Similarly, they gave out a DCF key for comparing with B hat. And this key output 1 on all points left of B hat and 0 everywhere else. And now if I add the outputs of these two functions, note that I already have arithmetic secret shares as the output. If I add these two, voila, I just get whatever I'm interested in computing. I actually get 1 exactly in region number 2. Okay. If I look at case number 2, things look a little bit different. B alone wrapped around, right? So B plus R, that is B hat, came around this side. So region 2 is the one that went around when I was doing the modular arithmetic. Right? Now, if I ended up doing the same thing, let's say I took the key for A hat and I computed the same thing. I took the key for B hat and computed the same thing. I end up with something, and this looks ugly. This doesn't quite look like what I wanted to compute. But if you stare at it for a moment, you'll see that it is what I wanted to compute, just offset by 1. That is, if I added 1 to my entire output, I actually end up with the exact output that I wanted. right? And note that this case, whether I'm in case 1 or case 2, is something that's known to the dealer, right? Because it depends on basically R, right? And B plus R, it depends on B hat, right? And so what the dealer can do is the dealer can provide a correction of 0 or 1. That is a secret sharing of 0 or 1 based on which case the P0 and P1 would fall into. And the two parties add that as well. And that ends up being the entire construction of BGI 19. Okay, so now here is our main technical insight. Recall that BGI 19 required 2 DCF keys for computing A hat and B hat, right? What we are going to do is we're going to take the keys for computing A hat and B hat and reduce them to a single key. We're going to use the key for computing C hat, where C is some point that is at least as large as B, larger than A. And that's the only thing, right? And we're going to give out only a single key and use that for both the comparisons, right? Plus some additional terms which don't require DCF keys, right? In fact, we will give out a universal DCF key for any or even all comparisons that you want to do on a particular input. No matter how many comparisons you need to do on that particular input, one single DCF key would suffice, as long as the endpoints that we are evaluating on or the comparison points that we are comparing on are public. So what's the magic over here? Let's talk about how to reduce comparison of X with A hat to comparison of X with C hat. The other case would be similar. If I look at the unmasked world, this is how the number line looks like. And again, in the masked world, I'm going to end up with 2 cases. Right? So in case 1, again, A hat and C hat don't wrap around, right? And so I look at X plus R. I'm going to break this into 4 regions, right? Region 1 is everything to the left of A hat. Region 4 is everything to the right of C hat, right? And in between, I'm going to call out a special point N minus 1 minus C minus A. And the significance of this point will be clear a little bit later. Now, let's look at DCF for A hat. And this is what I want to compute. And I want to compute something that is 1 below A hat and 0 everywhere else, right? But I don't have that with me. I only have a comparison with C hat, right? So what is it that I could potentially do? I could take my input and add C minus A to it, and then perform the comparison with C hat instead. What could possibly go wrong over here, right? Because I'm just shifting everything by C minus A, and I'm now, instead of comparing with A hat, which is what I wanted to do, I'm going to compare it with C hat. And now the shifted points look as follows. The regions also got shifted, and this this point over here ends up being A hat plus C minus A, which is actually C hat, right? And this last point over here was this special point, which was just N minus 1. And now if I evaluate this input that I have on C hat's key as well, I end up with something that looks like this, right? And if I stare closely, I observe that in these 2 regions, these 3 and 4 regions, I got the incorrect value, right? And why did I get an incorrect value? This is basically the portion over here that overflowed, right? And the overflow, if you observe carefully, it depends only on whether X plus R plus C minus A overflowed or not, right? And since both P0 and P1 have X plus R already with them, and they are adding C minus A, which is public, recall, they do know whether X plus R plus C minus A overflowed or not. And depending on that, they can add corrections themselves to this particular output that they have computed, right? And therefore, they can add this correction term -1 if it overflowed, and otherwise 0, depending on their inputs that were now local to them as well. And if I add these 2, observe that I actually get the right answer that I actually need. Everything is shifted on this line, but this is exactly the answer that I need. And the important point is that the overflow was local to find to both parties, and therefore you did not need any communication, nothing extra. Everything was done over here. And there's a second case as well, similar to the case of BGI 19, where things wrapped around. I'll not get into details of this, but it's pretty much the same way. And once again, you need another correction bit that's now known only to the dealer but that correction again can be given out by the dealer, similar to how it was done in the case of BGI 90. Okay. So with that, we are able to reduce all comparisons to a single key that we wanted to. For example, if I gave out the key for comparing with just the last point, let's say n-1, then I'm done. I can use it for comparing it with any public point, as long as it's the same input over here. And so because of that, even computing splines, even though it has so many intervals, if the endpoints are public, we can do all of those comparisons all with a single DCF key, and we don't have to give anything else. We need some additional correction terms, but nothing else more than that. Okay, I will now briefly discuss some of the end-to-end use cases that we have been successful in running. In very recent work called Llama with Kanav Gupta, Deepak Kumaraswamy, and Divya Gupta that will appear at PETS this year, we have new FSS protocols for zero-signed extension that I spoke about earlier, truncate, reduce, and also mixed bitwidth, splines, and so on. We get 4 Alpera functionalities and FSS protocols for all these activation functions, and we provide end-to-end FSS protocols for secure inference. I'll point out another recent work by Rifle, Toloniat, Panchaval, and Bach that also appears at PETS this year that also does end-to-end secure inference based on FSS without support for mixed bitwidth and splines and so on. But their focus was on using GPUs to improve performance and so on and so forth. And in a nutshell, here are some performance numbers. The performance of FSS-based protocols, as expected in the online cases, excellent. Online rounds, communication time, excellent. Key size, despite all our effort, is still the bottleneck. Example, for some of the large benchmarks that we are running, the key size can go up to 80 GB as well, right? But these are large benchmarks, but they can go up to 80 GB. In the last few minutes, I'll just tell you a little bit about the EasyPeasy system that we have built at MSR India. It's a fairly robust system that requires minimal cryptography knowledge to be able to run. Its front end can be TensorFlow or ONNX. We support a variety of backends, 3PC backend based on secure NN, a 2PC backend that has a combination of papers that we have written, CryptFlow 2 that did a whole bunch of different types of convolutions, ReLU, MaxPool, all those activations, the Siren paper that does all of these map functions and mixed bitwidth and so on. If you want a floating point arithmetic, secfloat paper as well. And finally, the FSS-based library as well, Llama, that we built recently. So this is our project webpage. I think the Llama code base alone is not yet up, but that should be up soon, maybe this month or so. And because we have built this robust end-to-end tool chain, we have been successful in running really large state-of-the-art machine learning models. For example, private personalized radiotherapy. So it's not just inference. You want to segment a tumor region in a 3D medical image. That's something that we have been able to do. This model is something like 1,000 times larger than anything that we have seen. So it's a really large model that we've been able to execute using MPC. This AI model validation that I spoke about at the beginning of my talk, that is also something that we've been able to do, where the test set was provided by a research lab called Caring Research, and Stanford AIMI built a model for predicting lung diseases based on that. And we could do it without revealing either data, just answer questions like, what is the accuracy of this model on this particular data? Out of the box, we could just take the models and run them, and that worked. So I encourage everyone to try out the EasyPeasy library, provide feedback, anything that you are looking for that is not covered by us. We are very, very interested in learning about use cases and things that we may not be aware of. And so would really encourage you to do that. Finally, this talk is dedicated to my dear ex-student Nishanth Kumar, who was a research fellow with us for 2 years. And the main result that I spoke about today, the Eurocrypt paper, also was joint work with him. He was a PhD student at UIUC with Dakshita Puranas, very unfortunately and tragically passed away a couple of months ago. And yeah, this talk is dedicated to him. Thank you.
Do we have questions? I will relay the questions so that you can hear.
One question that I had is, whether in this context of a 2PC or a multi-party computation, there is a difference from the case of homomorphic encryption. Well, you also need to quantize some functions. You also try to use table lookups and splices and things like that. If you know that there's like, specific differences that you can point to between these two cases, well, this technique applies here, but not there.
So the question was whether basically some of the techniques that you developed here also apply to homomorphic encryption, or what are the differences in homomorphic encryption approaches and this MPC approach?
Yeah, so I'm not aware of all the works on homomorphic encryption and the quantization and so on, but my understanding is that the quantization methods that are supported over here are much richer, just because the types of functions that we are supporting over here in terms of computing, things like both comparisons, things like computing sigmoids and tanh and so on and so forth. These are functions that are guaranteed to have, and we have those guarantees that the function that we are computing have 4 alps of error when computing that function, right? And to the best of our knowledge, even other MPC works, I think there is one mode in MP Speed's library that does support as low alp error as we do as well, but that has much higher communication than us. I think the one that's more efficient, that's based on polynomials alone, which perhaps homomorphic encryption would be suited to compute, that has like 5 orders of magnitude more error than what we have, and we have found it not suitable for any of our applications.
Another question? I can also come with a microphone.
No, if you abstract away the function secret sharing, what are the properties that we need from MPC or homomorphic encryption to support the optimizations?
So if you abstract away the function secret sharing, then do you have some simple to state properties that you need from MPC or homomorphic encryption to make your optimizations work?
I'm sorry, I didn't follow the question fully. Could you repeat that again?
No, I think maybe it's simple.
So was the question about if some of these techniques might translate to things like MPC and homomorphic encryption as well, or?
Yeah, well, what are the properties that you need from function secret sharing that you satisfy using function secret sharing that are required for your optimizations? And can you have the same?
Well, the important properties that we end up getting are that the online phase is like really fast, because we only have, for any function that we are computing, if it's a comparison, if it's a ReLU, if it's a spline, whatever it is, we have 1 round of online communications. And so everything goes into the pre-processing. So that is the advantage of it. The disadvantage is that everything becomes larger in the key size, which is what we are trying to reduce, and which is what we were able to reduce reasonably successfully in the European work.
Other questions? Okay, so let's thank the speaker again for the great talk.
Thank you very much.